In this video, we will derive the kinematic equations for constant acceleration in one dimension from calculus. If you're watching this video, I will assume that you're already familiar with the kinematic equations in one dimension for position and velocity from algebra. And of course, you know how to integrate. Before we start, I want to make it clear that the method presented here is completely general and can be in fact used for any time-dependent acceleration. So let's get started. We will assume, as I said, that the acceleration is a constant, that is, some real number, and also that the object has an initial position and an initial velocity at time t0, which we label by xi and vi. We then want to start by integrating the acceleration with respect to time and see where that leads us. So let's get started. We're going to integrate, first of all, the acceleration, a dt. And because this acceleration is a constant, we can pull it out of the integral like this. Now, I claim, before we even do the integral, that this is equal to the velocity as a function of time. How do I know that? From the units. The units of acceleration are, in the SI system, meters per second squared. And the units of time, of course, are seconds, which gives me a quantity whose units are meters per second, which is, in fact, velocity. So now we use the fact that the indefinite integral of a dt, if a is a constant, is a times t plus a constant of integration. Now, this tells us, therefore, that v of t is at plus some constant c. But we also know that at time t0, v of 0 is equal to v initial. So we can now set t equal to 0 in the above equation here and compare v initial to c. Clearly, if we set t equal to 0 in the above, the first term drops. The only thing left is the constant c, so we can also say that v of 0 is equal to c, which automatically tells us that the constant c represents the initial velocity. And therefore, we can say that v of t is equal to v initial plus at, where I have just flipped the two terms to make this equation be identical to the velocity kinematic equation that you obtain in the algebra-based class. Next, we want to integrate this expression here once again to obtain an equation for position. So once again, we integrate this equation, and I'm going to set it directly equal to the position. And the reason, again, why I know I can do that is because the units of velocity here are meters per second, and the units of time are seconds, which give me meters, which are units of position. But now I have an explicit expression for the velocity as a function of time. So I plug in that for v of t, and that tells me that I'm integrating actually two terms. The first term being v initial, which is a constant, plus the second term, which is at. Now I can split this integral into two integrals. So I can have v initial dt plus at dt. Again, the first integral is identical, this one here, to the previous integral that we just evaluated. And it just gives us v initial, which is a constant, times t. The second one is, I can pull the a out to simplify it. And it's the integral of t dt. Now, I know I said that you should be familiar with calculus in order to watch this video, but in case you don't remember, when you're integrating a polynomial, let's write it in terms of t to the n dt. In order to calculate this integral, you take the antiderivative, which is given by adding 1 to the exponent and then dividing the term by that exponent. So in this case, t is to the first power. So if we add 1, it becomes t to the second power. And we have to divide by 2. That means that we can write 1/2, which is the same as dividing by 2, times a times t squared. And to that, we add another constant, which we call d, so that we don't confuse it with the previous constant of integration. So this now is an expression for the position as a function of time, but we have to determine what the constant d is. And again, we're going to do the same thing. We're going to set t equal to 0 in the expression on the right, and because the first two terms depend on t, they cancel. So x of 0 is just a constant of integration d, but we said that x of 0 represents the initial position, which we label as x initial. So d is nothing but the initial position. And therefore we can write the expression for the position as a function of time as v initial t plus 1/2 at squared plus x initial, which we can also rearrange to make it look exactly the same as the expression that we obtain from algebra. So there you have it. This is the second expression, and these are the two equations for position and velocity as a function of time in one dimension. Clearly, these generalize to 2 and 3 dimensions because the 2 or 3 dimensions are decoupled from one another. So this will apply in the y direction or in the z direction as well. And as I mentioned at the beginning, this is a completely general method that can be applied to any acceleration that might be time dependent. And so in that sense, it's much more powerful because we can derive expressions for position and velocity even when the acceleration varies with respect to time, which is something that we could not do directly from algebra. So let's look at how we put all of this together in an example. Let's say we have a race car which has a constant acceleration of 3.81 meters per second squared. Find the car's position and velocity as functions of time if, at time t0, the car is at x equal 1.112 meters and it is moving with velocity v equal to 6.55 meters per second. I know that we could directly write the expressions, but for the sake of argument, let's go through the calculation by doing the integrals with the actual numbers. We're given that the acceleration is 3.81 meters per second squared. And the other two numbers here, because they're at time t0, they represent the initial position, which is 1.12 meters, and the initial velocity of the car at time t0, which is 6.55 meters per second. So in order to find the velocity, we start by integrating the acceleration, which in this case is just this number here, 3.81 meters per second squared dt. Because it's a constant, it gets pulled out of the integral, and so we just get a factor of t that multiplies that. And because now we know that the constant of integration represents the initial velocity, which is this number, we're just going to add it to it. And then if we want, we can rewrite the expression by flipping the terms, so it's in standard form, so to speak. So we have the equation for the velocity of this race car is given by this expression here. So we have found an equation for the velocity. Now, in order to find an equation for the position, we're going to integrate this expression here that we just obtained and then use the fact that the initial position is 1.12 meters. So if we integrate this expression, we're going to get the integral of 6.55 meters per second plus 3.81 meters per second squared t dt. Now we know that we get a constant of integration, and we know that the constant of integration is that number, so we don't need to go through the steps of resetting it equal to d and then setting it equal to that number. We already know what it is. So when we integrate this expression here, we get 6.55 meters per second times t plus the t dt gives us 1/2 times the constant in front of it, which is given by the acceleration, t squared, plus 1.12 meters. And again, this represents the position, and if you like, you can rearrange the terms so that the constant term is in front of it, but it really doesn't matter because no matter how you rearrange the terms in a polynomial, that polynomial is always the same. Here's a challenge for you. Repeat the previous example, but this time assume that the car's acceleration is not constant, but rather given by 3.81 meters per second squared multiplied by t. If you do that, you'll notice that both the position and velocity will have a different form. The numbers will be similar, but both the equations will have a different form. Thank you for watching, and as always, if you liked the video, subscribe and hit the notification button.